Hello. In this video, we will cover section 8.1, which is on an introduction to hypothesis testing. Suppose you heard a claim that a spun coin is biased because the head side of the coin sticks out. To test the claim, you spin a coin 20 times. The result is 20 heads in a row. This is surprising because you expected something closer to 10 heads. Based on that result, you think the claim is probably true. This is an informal example of a hypothesis test. An actual hypothesis test has the following steps. We start with a statistical statement about the real world. This statistical statement is then split into two hypotheses that have competing claims. In the informal example, the two claims would have been A spun coin is fair. This is the default claim. The default claim is always skeptical or status quo. And B, the spun coin is biased. After we go through and state our hypotheses, we collect or examine data relating to the statistical question. All right, in the informal example, this would have been the spinning of the coin 20 times and counting how many heads we got. In the third step, we analyze the data compared with our expectations. Our expectation is the default claim, always. In the informal example, this would be calculating the probability of getting 20 out of 20 heads when spinning a fair coin, which results in heads half of the time. Right, the probability is 2 in 1 million. And then step 4, we pick between the two claims. If the probability of an event is low, right, assuming that the status quo is true, then that suggests that the status quo was wrong and that the second claim is true. Okay, we're going to get more into that if that sounds complicated, but that is actually the basic idea of the hypothesis, of a hypothesis test. Hypothesis testing is about choosing between rival hypotheses. A hypothesis test starts off as a statistical statement about the real world, which is then translated into rival hypotheses that involve population parameters. Population in this context refers to population versus sample, that type of population, not people. All right, so population is all types, all things of a type. So for example, in coin spinning, the initial claim is that the spun coin is biased. This is a real world statement. We translate that statement into our rival hypotheses involving the population parameter P, right, which is the probability of getting heads when a coin is spun. Right, since parameter P is at the population level, not the sample level, it represents all spun coins. Okay, all of them, everywhere. All right, well, all spun coins, assuming that you're spinning the same type of coin. A fair coin has P equals 0.5. This is the default or the skeptical hypothesis. A coin that is not fair or biased has P is not equal to 0.5. All right, so the two hypotheses have names and symbols. The null hypothesis, represented as H with this sub-zero, typically pronounced H naught. This is the default, the status quo, or the skeptical hypothesis. In the context of research, the null hypothesis often represents no change, no effect, or no difference. The null hypothesis always uses the equal sign. And then the second hypothesis is the alternative hypothesis, represented as H sub A, or HA. This is the research hypothesis. It's the hypothesis we're interested in testing whether it is true. All right, so just to put it all together, for the coin spinning experiment, this is, at the bottom of the page there, that is what the two hypotheses look like. You've got H naught, P equals 0.5, HA, P is not equal to 0.5. All right, so let's look at an example. So historically, about 70% of all US adults were married. A sociologist who believes marriage rates in the United States have declined takes a random sample of US adults and records whether or not they are married. State the null and alternative hypotheses in words, then state using symbols where P is the proportion of all adults in the United States who are married. All right, so the null hypothesis is going to be the status quo. All right, so the status quo is 70%, so we would say the proportion of adults who never married is still 70%. And then the alternative hypothesis, that is that the sociologist's research is correct, or their theory is correct, and that the proportion of adults who never married is less than in the past, or less than 70%. Written in symbols, we've got H naught, P equals 0.7, so we're writing percent as a proportion, and then HA, P is less than 0.7. So those are the rival claims. Let's look at another example. So homework example. A recent poll estimated that 2.4% of American adults are vegetarians. A nutritionist thinks this rate has increased and will take a random sample of American adults and record whether or not they are vegetarian. State the null and alternative hypotheses in words and in symbols. All right, so the null hypothesis is the status quo, that the percentage has not changed. So we would say that the percentage of Americans who are vegetarian is still 2.4%. All right, and it's written there, H naught P equals 0.024. The alternative hypothesis is that the nutritionist is correct. The percentage of Americans who are vegetarian is greater than 2.4%, and it's written there, HAP is greater than 0.024. And one more example. A law association estimated that 82.5% of law school graduates last year found employment. An economist thinks that the current employment rate for law school graduates is different from the rate last year. Pick the correct pair of hypotheses the economist could use to test this claim. The key word here is different. So it's not greater than, it's not less than, it's different. But when you see different, you want to use not equal to. All right, so in the alternative hypothesis. So our two hypotheses would be H naught is that P equals 0.825, and then HAP is not 0.825. Okay, and so I made this slide before I added the homework examples, so it's the first sentence is a little wonky. But so notice the previous examples, we had a bunch of different types of inequalities for the alternative hypothesis. It turns out there are three different types. All right, there are the three possibilities. We go through and say the claim is either greater than the status quo, and you use a greater than symbol, less than the status quo, use a less than symbol, or it's different from the status quo, and you use not equal to. The first two, less than or greater than, are called one-sided hypotheses. And then the third case, the not equal to, is called a two-sided hypothesis. This is going to matter in the next section. It doesn't matter in the rest of this video, but it will come up again in the next section. You need to do something slightly differently depending upon whether you have a one-sided or a two-sided hypothesis test. Okay, this is a very, very important slide. So hypothesis test, let's talk about benefit of the doubt. Hypothesis tests are like criminal trials. In a criminal trial, the defense is given the benefit of the doubt. The same is true of the null hypothesis in a hypothesis test. The null hypothesis is given the benefit of the doubt only when an observed result or data is extremely unusual, assuming that the null hypothesis is true. Do we reject the null hypothesis and accept the alternative hypothesis as true? All right, so this is the core idea behind a hypothesis test. When you do a hypothesis test, you take the null hypothesis, you take the status quo thing, you assume that is true. All right, so you start off with that, and you assume that's true. Then you go through and you run an experiment. And if the results of that experiment does not make sense, you get an extremely unusual outcome, assuming that the status quo was true, then you can go through and say, oh, you know, maybe the status quo wasn't accurate. Maybe that status quo wasn't true. All right, so let me go over that again. You start off, you assume the status quo is true, you do something, and then if the outcome of that thing is really weird, all right, assuming the status quo is true, then you come back and you say, maybe the status quo wasn't true after all. All right, and that is the idea behind a hypothesis test. So that is what you're going to see consistently throughout the rest of this video and throughout the next video, is going through and doing that type of thing. All right, so significance level. It is possible to reject the null hypothesis and be wrong, right? So for example, we might go through and reject the hypothesis that a spun coin is unbiased because we get that 20 heads and 20 results and 20 spins. So we go through and we do the 20 heads and 20 spins, and we're like, no way, there's a 2 in a million chance of this happening. So there's no way this coin could actually have been fair. There's no way I could actually spin a regular coin 20 times, okay, and get heads 20 spins in a row unless the coin is biased, okay? Well, it turns out you could, it happens 2 in a million times, but 2 in a million events do happen. Okay, and so you might have been wrong. So the significance level is going through, and that's the probability that that happens. It's the probability that you're wrong. It's the probability that we go through and we say that the null hypothesis was wrong, and it turns out the null hypothesis was correct. All right, so to use the criminal justice equivalent, the significance level is the probability that we say a suspect is guilty, and then it turns out that they're actually innocent. So let's look at an example here. So an internet retail business is trying to decide whether to pay a search engine company to upgrade its advertising. In the past, 15% of customers who visited the company's website by clicking on the advertisement bought something. This is called a click-through. The search engine company offers to do an experiment. For one day, a random sample of customers will see the retail business's ad in a more prominent position. The goal is to test whether this will increase the percentage of click-through customers. In that case, the rival hypotheses are H0 is that P equals 15%, and HA is that P is greater than 15%. All right, but the question is not about the hypotheses, it's about the significance level. The question is, the test is conducted with a significance level of 5%. Describe what that significance level means within the context of that problem. Okay, so the significance level is the probability that you reject H0 and it turns out H0 was true. All right, so in this case, it says that the probability is 5% that the company rejects that the proportion of click-through customers is still 15%. That's the null hypothesis. It rejects the status quo. It concludes that the alternative hypothesis was correct and that the proportion of click-through customers has increased, but it's wrong and the proportion was actually still 15%. So that is what the significance level is. All right, so it will make sense with more information. Okay, so let's talk about typical significance levels, and I can provide more background that will maybe flesh it out and make a little more sense. The significance level that most researchers and statisticians use is 5%. Why? The significance level is how often we make mistakes. It's how often we choose to reject the null hypothesis when the null hypothesis was actually correct. It represents how careful we are being in the hypothesis test. So why not be more careful and choose a number smaller than 5%? I mean, who wants to be wrong 5% of the time? Let's be wrong 1% of the time. Well, the flip side to the significance level is it is the threshold to choose between the null and the alternative hypotheses, right? We've got our competing hypotheses, and it is the threshold to choose between them. If you set too high a threshold, then it becomes too difficult to prove that the null hypothesis is wrong. We are being too careful. So one way to view it is as the amount of evidence that is needed before we choose between the null and alternative hypothesis. Recall that the null hypothesis is given the benefit of the doubt. The significance level is how much evidence we need before overcoming that benefit of the doubt. With a 5% threshold, we need to show that an observed result, right, so from an experiment, so we go through and we do an experiment, needs to occur less than 1 time in 20, assuming that the null hypothesis was true, all right, to overcome that benefit of the doubt, reject the null hypothesis, and accept that the alternative hypothesis is actually true. And if you think about that, that's a reasonably high standard. So if you go through and you say, all right, I think the null hypothesis is true, I'm going to go through and I do an experiment. That experiment, the outcome of that experiment, you need to show that that outcome would only happen less than 1 time in 20 before you'd be like, maybe that null hypothesis ain't right. Maybe the alternative is the right one after all. Okay. Now, if you think about that, a 1 in 20 event, that occurs pretty rarely. All right. So it should be unusual for you to do an experiment and get that outcome. Right. And so because of that, we consider that to be a reasonably high standard. Now, can you have 1% significance levels? Yes, you can. Under certain circumstances, you can use a 1%. Sometimes you see as high as 10%. That's usually the range, is between 1 and 10%, and 5% is the norm. Okay, so how do we measure how much evidence we have in order to pick between the null and hypothesis, the null and the alternative hypothesis? And that's another way of saying, how do we measure how often an observed result occurs given that the null hypothesis is correct in order to make a decision between the two, right? How do we figure out whether we've got that 1 in 20 event or not? All right, so there's 2 steps to that. First, we go through and we calculate the z-score for the observed result. All right, so the z-score, this is a classic z-score from earlier in the course. All right, so z-score equals, and you do p hat minus p sub 0, p naught, over the standard error. And then the standard error looks pretty similar to the normal formula, except you've got the p naughts here. So what are these things? The symbol p naught comes from the null hypothesis. So we assume the null hypothesis is true, and we calculate the standard error using it. All right, and then afterwards we take all that and we put the so the p hat comes from the observed result, comes from the experiment that we do. It's like the spinning coin, right? So p hat is going to be the proportion that we get from our observed result or from our experiment, and n is going to be the number of trials we do. So in the example earlier, so if we spun a coin 20 times, that would be n is 20, and if we got 20 heads, the proportion of heads would be 100%. So we would use 1 in place of p hat. Okay, and of course, the next slide, I get into more detail. So suppose we're checking coin fairness. We spin a coin 20 times and get 7 heads. What would the test statistic be? All right, so first, in that case, if we're spinning a coin, a fair coin has results in heads 50% of the time when you spin it. So P naught would be 0.5. And then from the experiment, we got, so 7 out of 20, we got 7 heads out of 20. That proportion would be 0.35. And since we spun the coin 20 times, that would be n equals 20. And then we take those 3 things and just plug them in. And you get the standard error is 0.1118. And the z-score is negative 1.34. Okay, so we interpret the test statistic exactly as we would z-scores from earlier in the course. The result of p hat minus p naught or p sub 0 is how far the observed result is from the null hypothesis, where the null hypothesis acts like the mean. So we're finding the distance between these two events. So if we expect that 50% of the coin spins are going to be 0.5, then we put 0.5 in here. So it's our expectation, our status quo, our null hypothesis is in the formula. And then we compare that with the result that we actually got when we went through and did an experiment, when we did an experiment, yeah. So we go through and we take the difference between those, and that shows how far the result of our experiment was from our expectations. Okay, so that gives us a distance, but to interpret that distance, we need to go through and divide by how much error, how much distance is there typically between experiment results. And that's where the standard error comes in. So we go through and we divide by the standard error. It's the same idea as going through and dividing by the standard deviation. And so when you do that, it enables you to take the distance between your expectations and your actual result, divide by how much error there, how much distance there usually is between them, and we can come up with a score for the experiment, for the observed result, that is in terms of the number of standard errors that we get away from the null hypothesis. So if you spin 7 heads in 20, if you get 7 heads in 20 spins, and that gives you a z-score of negative 1.34, we can translate that into, that's 1.34 standard errors below what we expected, assuming the coin was fair. All right, so that's the way you can go through and interpret the test statistic is in terms of z-scores and the number of standard errors that your experiment result or your observed result was away from what you expected. All right, so if the null hypothesis is true, all right, then we are going to expect that our test statistic is going to be very close to 0, right? So the idea being, if you expect to get, if your null hypothesis is true and you do an experiment, then the result of the experiment should be very close to the null hypothesis. So these two things should be very close together. Okay, if you're expecting 50% when you spin a coin, then you should get close to 50%. And then when you subtract the two, this quantity should be close to 0. All right, and so that's the idea here, is that if the null hypothesis is true, then we expect the test statistic to be close to 0. All right, so let's look at a test statistic example. Economists agree that 2005 was the year in which the greatest percentage of American households owned their own home. The percentage that year was 69%. This percentage plummeted during the Great Recession from 2007 to 2009. Recently, economists wanted to test whether the housing market had recovered. Pew Research conducted a random sample of 2,000 households that showed that 63.5% own their own homes. And they want us to go through and find the test statistic and explain the result of the test statistic in context, like in context of the problem. So we just take all the stuff and just plug it in. All right, so first calculate the standard error. So you take the 69%, which is what we're assuming the population is, plug that into the standard error formula, then you should get this result. And then take that result and plug the 63.5 and the 69% into our z-score formula, and you get negative 5.32. All right, so what is that? So we're saying that the z-score, or the result here, is 5.32 standard deviations below what we expected. Or sorry, standard errors. So it's 5.32 standard errors below what we expected. Now recall what you remember about standard deviations, because standard errors work the same way. So 1 or 2 standard errors is a small amount of standard errors, right? So you've got 68% of the data is within 1 standard deviation, 95% is within 2 standard deviations. So 5 standard deviations is off the reservation. It's miles and miles and miles away. And so a z-score of negative 5.32 is very, very far from 0. All right, so this makes it very unlikely that the home ownership percentage is actually 69%, right? So if a z-score close to 0 tells you that the null hypothesis was correct, then a z-score far from 0 is going to tell you that the null hypothesis was incorrect. All right, let's look at another example. This one's from the homework. A college chemistry instructor thinks the use of embedded tutors will improve the success rate in introductory chemistry courses. The pass rate for introductory chemistry is 57%. During one semester, 200 students were enrolled in introductory chemistry courses with an embedded tutor. Of these 200 students, 115 passed the course. What is p hat, the sample proportion of students who passed introductory chem? What is p naught, the proportion of students who passed chemistry if the null hypothesis were correct? And then find the value of the test statistic and explain the resulting context. Okay, so before we jump to the next stage, so p hat, that comes from the experiment, right? That comes from the observed result, right? So what was the experiment here? Well, we had 200 students take introductory chemistry with an embedded tutor. So you want p hat as a proportion, so you want to divide these 115 by 200. That's going to be p hat. P naught, that's the percentage that we're assuming. That's the default. That's the status quo. It's the current situation. So what is that? That's 57%. All right, and then find the value of the test statistics. So that's just plugging it all into those formulas. All right, so you can see here, question A, take 115, divide by 200. Question B, 0.57. And then question C, oops, I don't know why question A is still there. Question C, plug 0.57 into the standard error formula first, then take that result and plug it into the z-score formula, and you get 0.14. And so to interpret that, we're saying 0.14, the result is 0.14 standard errors above the null hypothesis. Because it's positive, it's above the null hypothesis. That's pretty close to 0. So that would suggest, that outcome would suggest that the null hypothesis was correct. All right, so interpreting the test statistic in terms of probabilities, that's another type of interpretation. So once we have the test statistic, we can go through and use it to find the probability of getting a result that is that level or more, or anything more extreme. Right, this would be the probability that of the observed result from your experiment, given that the null hypothesis is true. So again, we start off, we say the null hypothesis is true, we do an experiment, and then we want to know what is the probability of getting that outcome. And then if the probability is low, then we'd say, okay, well, the null hypothesis probably wasn't correct if we assumed that was true, and then we did an experiment and got something that shouldn't happen, right? Where the probability is small. All right, so we need to go through and be able to calculate what the probability is, and that's the p-value. So the p-value is the probability. If the p-value is low, then that means that the probability of the observed result was low, given that the null hypothesis was true, which suggests the null hypothesis wasn't true. That's what I just said. I really should just read off my slides. So we will calculate p-values in the next section. So we're not going to do it in this section. But for now, the only thing that matters are the 2 above points. These are the 2 above points. So once we have a test statistic, we can go through and turn that into a probability, and that is going to be the probability of getting that result from the experiment you did, the observed result, given that the null hypothesis was true. Once we have that, we can actually then look at that probability and do some interpretation with it. If that p-value, if that probability is low, then that means the probability of the observed result was low, given that the null hypothesis was true, which suggests that the null hypothesis wasn't true. If you assume something's true and then you get an outcome that shouldn't happen because it's got a low probability, then that suggests that your assumption was wrong. All right. And then we'll talk about more about p-values in the next section. All right. And then last but not least, another homework example. A college chemistry instructor thinks the use of embedded tutors will improve the success rate in introductory chemistry course. This is a different question than the earlier one. The passing rate for introductory chemistry is 66%. During one semester, 200 students were enrolled in introductory chemistry courses with an embedded tutor. Of those 200, 146 passed. The instructor carried out a hypothesis test and found that the observed value of the test statistic was 2.09. So you got 2.09 standard errors above what the expectation would be if the percentage was only 66%. He went through and calculated the probability of that. Again, we haven't explained how to do that yet, but this chemistry instructor knew how to do it. Went through and calculated the p-value and got a p-value of 0.0183, so about 1.8%. There's a 1.8% chance that, okay, I'm sorry, I'm skipping ahead again. Let me read off my slide. So explain the meaning of the p-value in context, and then based upon this result, should the instructor believe that the success rate has improved? All right, so there's three things they want us to do. State the hypotheses that were used for the test, explain the p-value in context, which I just started to do and interrupted myself, and then should the instructor believe the success rate has improved? All right, so the hypotheses are the rival hypotheses. One is the status quo, that the proportion is still 66%. And then the other one is that it is actually improved, that embedded tutoring actually made a difference. Explain the p-value in context. So what is the p-value? It's the probability that you'd get 146 or more students who would pass out of 200. It's the probability. I can't even read off the slides. So what it's saying is that there's a 1.83%. There's a 1.83% chance that you'd get 146 out of 200 students passing, assuming that the success rate is 66%. Right? It's the probability that you'd get an outcome from the experiment, assuming that the null hypothesis was true. All right, so 1.8%. There's a 1.8% chance that 146 out of 200 students would pass if the null hypothesis is correct and the pass rate is actually 66%. Okay, the last way I stated it was the best of those. All right, and then question C, should the instructor believe the success rate has improved? Yes. If the p-value is small, then that suggests that the null hypothesis was false. All right, that the null hypothesis was wrong. If you go through and you assume something, you assume the pass rate is 66%, and then you get a much higher pass rate than that, okay, then your assumption was probably wrong. And the pass rate is probably not 66%. It's probably better than that. Okay, and so that really gets to the heart and core of a hypothesis test. Okay, thank you for watching. That's the video. The next one is more on hypothesis tests. This is just an introductory video, and in that video, we'll calculate p-values and do a bunch of hypothesis test examples from beginning to end. All right, thank you for watching. I'll see you next time. Bye-bye.